Greetings, everyone. Thanks for joining. We're on 8.8 in our second discussion on Chapter 4. So, one question was brought up that we'll definitely come to, but is there just anything else that anyone else wants to add about 4? Any just reflection or any question that's kind of surfacing that we want to add to the stack? All right, let's go to the message passing. Okay. So in message passing, is there a decay of information as the distance between the variable X and individual Markov blanket constituents increases? Is implementation of information decay in message passing an option for model implementation? Who wants to give a first thought on that? Or any other kind of curiosity around it?
So I'm not sure if I'm understanding it very well other than intuitively, but would it be the case that information decay wouldn't necessarily, I suppose, make sense here, given the models are already working in terms of like time steps, and so you're already kind of you're recomputing your gradients and your posteriors and so on in every given time step, such that the idea of some kind of holistic piece of information that's being carried from time step to time step doesn't quite make sense. That is, each time step involves an entire set of like recalculations. Does that make any kind of sense?
Yeah. So just to start with, one uncertainty is I'm not exactly sure about message passing in the continuous versus discrete time setting. Again, hopefully something that we can unpack and talk to Magnus Kudal et al., since I know that he's an expert on the continuous time setting. But any other thoughts on this, or I'll try to give an answer. Ali?
Yeah, just one quick note about message passing is, before going into the details of how exactly message passing happens in Active Inference Framework, it's probably worth noting that it's inversely proportional to the robustness of any self-organization systems, because you see, if we consider an agent and its peripheral systems or peripheral let's say limbs as a kind of fully centralized system in which the message passing happens almost in a fully centralized way from the brain, or the central processing unit, onto the limbs, then this system would not be as robust as the system in which this kind of message passing is distributed among the elements of the system. So I think that's one of the reasons why we see signal decay, or the loss of information, as we go up to the hierarchy. And the more we go up to the hierarchy, the less precise the information becomes. But in order to have more and more precise information, we need to somehow acknowledge a kind of autonomy onto the peripheral nervous system, as opposed to central nervous system. So that's one of the ways humans nervous system is organized, in which this kind of distribution of agency, autonomous agency is distributed among both peripheral system and the central system. So, coming back to active inference framework, I also believe in this framework, it beautifully captures this kind of hierarchical model, because obviously, as we move farther away from the peripheral elements of any system, the elements which have direct access to the not direct access, but closer access to environment, then the accumulation of probabilistic errors becomes larger and larger. And that's why, in order to have reliable information, we need to discretize these kinds of information at some point without necessarily having to take into account every single bit of information that we receive. So on the lower levels of the, when we're dealing with the lower level systems, we mostly deal with continuous time models, which allow for more precise kind of formulation of message passing. But as we go up to the central nervous system and conceive discretized elements of organization, such as cognition, emotion, and so on, or decision making, this process becomes much more discretized. So that's basically the idea behind the hybrid models of active inference, in which we can incorporate both continuous time and discrete time elements into a single system.
That's awesome. Thank you, Ali. Alexi?
I wonder if I can ask you, Ali, to clarify. So let's imagine that I'm a shark, right? And if I go up the hierarchy of beliefs, then perhaps the most firm, coarse-grained belief is that I will survive. One step down from that is that I can breathe in water, right? So as the message comes up in the hierarchy, I don't need as many details, like because these are not going to change. If they change, I die. Is that kind of what you're saying? That if
exactly, okay. Yes. Because as you said, as we go up to the hierarchy, we'll need much less detail, and we just need to take into account, the general gist of the information we get in order to survive, or I don't know, achieve a goal or something. But obviously, if we want to, take into account every single detail of every endeavor, we'll need much more precise channels for information passing.
Mm-hmm. And if I may, one more quick question. In chapter 5, they make a point to say that ascending messages, which are prediction errors, are usually higher frequency than descending messages. I mean, they declare it, but I didn't exactly see where they take it from. And so I was trying to, they illustrated with a cortical column, and I was thinking that, indeed, this is very interesting research that we have top-down messages that are, beta rhythm or something like that, and they govern the gamma, which is higher frequency. Could you talk a little bit about why prediction errors and ascending messages are higher frequency nonlinear functions?
Okay, on this question, I can only take a guess because I don't honestly know the exact answer, but I believe the reason that the ascending information is, they're on a higher frequency level than, the descending information is because, again, coming back to this hybrid model of continuous time and discrete time, ascending information kind of deals with, let's say, a continuous discretization of information. And that's why, as we go up in the hierarchy, we'll need to have a much more, much higher frequency for the information gain, because we need to we need to construct those discrete information as quickly as possible, and based on those discrete elements of our information, we can then infer any necessary prediction, any necessary information about the error that we get, or any other kinds of manipulation or optimization we need to take into account. And I believe this kind of bidirectionality maps quite well on adaptive resonance theory, Grossberg's adaptive resonance theory, because in that theory as well, this kind of bidirectionality between the ascending information and descending information comes in a kind of resonance, and they adjust their frequency as to become the resonance fully cyclic passage for information, both going up and going down. So that's why I believe in this kind of framework also it's necessary to take into account different rates of frequency for both ascending information and descending information in order to allow for this kind of resonance to happen between those two lanes.
This is awesome. It's a lot of great information. Let's try to add a few pieces because I think there's different aspects here. So first, Ali, you pointed to the topology of message passing. Messages are being passed on the topology of the variables. So how the variables are connected is how the messages are being passed. Sounds kind of circular, but that's the whole reason why this box discusses basically the Markov blanket, which is just describing any given node is going to be surrounded by a blanket for that node. There's not an absolute tag on a given node, so it can't be said just singularly this node is an internal state or a blanket state, only with respect to the whole partition. But that's why two message passing strategies are being described directly alongside the Markov blanket. So a lot of times we see that particular partition in active inference, or just more broadly, we see a Bayesian graph and how the variables are connected. And this is going to be an implementational or operational procedure that's going to compute what it's going to turn the crank one gear for a given topology of connectivity. So this point about the robustness is similar to the robustness of a distributed system. I mean, if you have a fabric with only local connections, then it may take some time to propagate or percolate with the information. But on the other hand, there's not a single node of failure and all these other features. Message passing graphs can include discrete and continuous time and discrete and continuous state spaces. Like all of these different variants that we've been discussing play nicely together. Chapter 8 comes back with a hybrid model, and livestream 46 on the folk psychology, where in the periphery, it's more like continuous sensation and action. And then as you get towards like the cognitive decision-making states, you're dealing with discretization. Okay. Another point is about like the computational tractability. So there are works like this one from 2019 with Parr et al., where let's learn more about the technical details. But basically, there's a few different flavors of this message passing implementation that are also kind of hinted at in the box. But suffice to say that, like, for a given topology of a Bayesian graph, which might be describing a cybernetic system, ActInf agent, or it could just be any other Bayesian graph. This isn't about perception and action specifically, but on any Bayes graph, you can basically define an implementational procedural pseudocode for how to just bring it that much closer towards harmonization, where if it's kind of the ball is already at the bottom of the bowl, it's not going to go anywhere. But then if it's not at the bottom of the bowl, from like a variational inference perspective, it will go there. And there's a procedure for doing that that's tractable. Why is the frequency higher on ascending messages than descending? So first, these kinds of phenomena constitute empirical evidence for hierarchical predictive processing architectures, but the framework doesn't depend on these phenomena being the case for our real nervous systems, but they're always nice to find. And there's a few ways to go here. One, connections with the Nyquist frequency. So this is, if you're going to be sampling from vinyl, from analog, then that's a smooth curve. That's the continuous time. That's like the motor perception. That's the peripheral nervous system. That's the record. That's like a clock with a smooth moving minute hand. And then you're going to have it translate to digitization, like you're digitizing the record. So if there are top-down predictions like about the hour in the clock metaphor, we could have ascending predictions about minutes and descending predictions about hours happening every clock cycle. There's no reason why you wouldn't do that, but at the same time, you can bake in this structural understanding that hours are top-down and slower, which is consistent with more broadly in nested modeling, nested outer layers, deeper, however you want to think about it, like they are slower and bigger. So you only need to send down that hour expectation more infrequently. And then just lastly, like signal decay. If you have a Markov chain, so let's just think really simply about some just without bringing action too much into it, think about just the perceptual part here. So just like the music listening example that I think is in 7. So here we are. This is a partially observable Markov process happening through time, emitting an observation. So it could be the temperature changing in the room through time, but we're not intervening. So no action yet. Imagine if B were the identity matrix, like all ones on the diagonal, you would just be carrying S forward with perfect fidelity. But if B were like 0.7 on the diagonal and then 0.1 on the off diagonal, which is like what the case that it was in the music example, then you can, if you set up 100 of those runs next to each other, it'd be like the signal was kind of like blurring by 10% each time. So the signal, it depends on like if there's a degradation of the signal as it's being passed. Here it's being passed in time. If it's being passed noiselessly, then the signal propagates more distantly in space and or time. Whereas if the insulation around a node is such that it blurs half the information upon its immediate exit, then that's like then that information, like that perturbation of the Bayes graph, it just dampens more rapidly. Ali?
Thanks. That connection to Nyquist frequency was really insightful and helpful. But to add to your point here, I also believe that if if there wasn't any gradation of frequency between those two paths of information passing, I believe something like an aliasing effect would happen if the brain or any kind of agent wanted to reconstruct the information from the input system and then produce the necessary output system, because I mean, it's necessary to somehow distinguish between the kinds of, I mean, the frequency of incoming information as opposed to the frequency of the reconstructed information in order to evade these kinds of aliasing type effects, which obviously would be undesirable.
Yeah, cool. And also ties to the ultimately the audiovisual roots of predictive processing. It was not generated to describe or explain biological phenomena. It arose in the 70s, 20 years before Rao and Ballard, 1999, in the context of maximum information compression for audiovisual. And then the other sort of connection back to the more like bodily, maybe a book that some of you are more familiar than I, but The Body Has a Head. It's kind of like a exploratory narrative biology, physiology book. But of course, the title is the provocation about the body's primacy in, I guess, what we would say action and inference. Alexi?
Yeah, I wanted to reflect on what you and Ali said about the Nyquist frequency, and also going back to, please forgive me, sending messages, prediction errors, high frequency. If we take this evolutionary kind of thought that, you know, the higher in the hierarchy I go, the more difficult it is to update a prediction. They're more well entrenched, right? So let's imagine that I'm a rat and I have an inborn phobia of cats. You know, one strand of cat hair, you know, causes freezing. But if I'm in the environment where there's mortal danger, like a trap, and the only escape route smells like cats, then I have to update that very firm prediction to get out. So it takes high energy, which in like Planck's equation means high frequency, to update the high level predictions. I know it's very speculative, but what do you think about that?
Yeah, I think there's a few ways that you could model that. Like let's just say we have an aversion to cat smell. Like it's a negative value in C, or it's a lower value in the C vector, just to be clear. Like we're talking about some sensory vector. And there's, in our generative model, we have some value that just is called cat smell, and we prefer it to be lower. Well, if there are two paths on the maze, then to take the path with the cat smell, it has to have pragmatic or epistemic value. So if we have a 10-to-1 aversion to the cat smell, but then the expected free energy of the cat path is greater than 10-to-1, then you could think about that as like the circumstances reflected by the epistemic or the pragmatic value of a course of action, but the circumstances would lead to selection against that. There's probably other ways that it could be explored. One would, yeah, but yeah, higher, or so, and there may or may not be these kind of, it may or may not be an option. Like I'm thinking about trying to see two colors as indifferent when you can clearly see them as different, or something like that. Like you're going to butt up against some fundamental, like the wavelength of light, or like maybe there's a sound that maybe, you know, some sounds are maybe culturally aversive or not, or pleasant, but maybe there's also just a volume or some type of sound that it's like, yeah, probably you can't can't. But then again, if that was the only path to escape a burning building, then that kind of stuff would happen. So then I think you got to zoom out beyond the single dimensional generative model, and then consider a more holistic generative model. Like we have 10-to-1 preference against cat, but we have 100-to-1 preference for blood glucose. So then right there, you've constructed a generative model that enables you to make risky decisions.
Thank you. That's very, very useful.
Yeah, and in the end, it's not about the rat. That's the territory. It's about the generative model. So different modelers may construct different generative models that display certain kinds of behavior or not. So we have the portfolio of models, and then we ask, well, what experiment is going to help us update our attention to these different models? And someone has one where there's only, cat smell, yes or no. Somebody else has no, a little bit and a lot. Somebody else treats it like a continuous variable. None of those are the true map, but we have all the maps on the table, and then that allows us to design the experiments or the circumstances that would differentiate the unique predictions and explanations from those maps. Ali?
It also reminds me of Terence Deacon's nested conceptions of information. So instead of representing these kinds of hierarchical relations as higher order or lower level, lower order processing of information, he represents them as three nested kinds of information, in which the Shannon information would be the most basic one, and then referential information, which is he also refers to as aboutness information, incorporates a kind of medium susceptibility to any error, and it is an emergent information rising from those Shannon information, and ultimately we come to significant information, or in other words, information about usefulness, which is what actually dictates how the survival of the species ultimately is determined. Through the evolution and so on, and it incorporates a kind of the connection or association between the reference of that usefulness information and the teleodynamic requirements of the species is what dictates what would happen in the significant information, or in terms of FEP, the minimization of free energy.
Nice. That's awesome. Yeah, information is like one of the most overloaded terms, or just loaded terms. But Shannon, 1948, studying signal transmission in the telegraph networks. So it has to do with that pure Morse code level of being able to distinguish like a signal from noise, and then projecting all that down to the Shannon entropy. And then to the extent that a signal can be detected from noise, which is about the observer, not the system in itself already, then there's this like semantic or symbolic information. But symbolic or semantic information, if we're going to continue with this evolutionary line, like, okay, so here are the photons. We can pick out the signal and the photons, a signal and photons. It looks like it's yellow and red. Is that a good caterpillar to eat? So one has to go beyond the kind of Shannon information. If you just had the entropy, Shannon entropy of different natural settings as a bird, that's still two structured jumps away from like, should I go for this caterpillar or not? But a lot of times this is taught as information theory, kind of the beginning and the end of information theory, when this is the syntactic information and then the semantic. But the abstract semantic is still not the actionable information. Let's see, someone has added the key things, how you define the Markov blanket. I mean, yeah, but we're not playing with the definition of what a Markov blanket is. Maybe this could be rephrased as the key thing is around which node you choose to highlight as your system of interest, call it internal states, and then the Markov blanket is trivially defined around it. i.e. there's a partition between whatever, or there's no partition. Well, again, if you're using a plural, there is a partition between them. That's what makes you think that they're two different things. And everything under the, or there's no partition and everything under the blanket's conditionally dependent. Well, the fact that you have modeled a blanket or a partition at a given scale doesn't preclude there from being, as they say, message passing within the same blanket, because blankets are not something fundamental. It's like saying, could messages be passed inside of California? Yeah. But then also you could go to the county level, and there could be messages between the counties or between the cities or between the agricultural objects within the region. I've not seen this, would love if somebody pointed me references. I'm not sure exactly which exact reference, but more broadly, nested Markov blankets could look to the kind of Earth systems modeling or our variational eco-evo-devo paper. Nested Markov blankets, they're having message passing within and across. And the kind of like lateral, same type of thing, same scale, message passing. And then now that you passed all the messages amongst the states, and now we're in California. And then you pass all the messages amongst the counties. And then, but I don't have a specific reference where that is written out. But yeah, what an interesting question. And message passing is so cool because it really connects like this. But what if this was just an abstraction and there wasn't any procedure known for how to compute it? Then you'd have kind of like the blueprint of a building, but it'd be awesome if you could build it. But in fact, this is the blueprint, and the blueprint can basically be rendered or operationalized into a procedure. So that is a super, super strong connection, and also one that's not unique to active inference. Although I as far as I know, the 2017, this paper, I believe is far more general. So somebody can add more here, but basically, here's the continuous and the discrete representations. And in this paper and some other one from this era, like they showed that every Bayes graph has a Forney factor representation. And then previously it had been shown that every Forney graph had a message passing implementation. So in this paper or some other one, like it kind of connected all the pieces up and said, yeah, now there is a message passing procedure on arbitrary Bayesian graphs. Again, that doesn't have to be about even a perception action system. I think it just made the general case. So message passing is definitely important. And also it's another example of like, perhaps even a difference in practice between like deep learning, reinforcement learning, machine learning, AI, and active inference to the extent that the distinctions can be drawn. Just to highlight, because there's of course multiple differences that we've talked about, but a lot of the work in AI and ML goes into like figuring out the implementational detail, like kind of getting in there with the specifics of the model. Whereas once something is stated as a Bayes graph, then it's kind of like standard methods. Like you don't need to intervene in how your source code is compiled. And so similarly, the message passing step kind of compiles it into a procedure, but you don't need to step in to fine tune how the blueprint goes to the construction, which I believe is a great advantage. Anyone want to go to a specific question, or we'll just try to look? There's so many questions on chapter 4, so anyone can just like bring up one or some topic that they thought was cool in the chapter.
Actually, I did want to briefly just kind of harken back very quickly to something Ali brought up earlier, which is adaptive resonance theory, and maybe how it relates to the asymmetrical frequencies found in message passing. And I know in chapter 5, where we start discussing kind of, or we start seeing more discussion of like neurobiological correlates and things like that. You know, there are these references to nonlinear functions being involved in the computation of prediction errors, such that what is it? Ascending messages tend to be much higher in frequency or faster than descending messages. I mean, are all of these things kind of related? You know, as far as message passing goes, I'm rather into things like fMRI and EEG analysis, and so I kind of have a personal interest in the asymmetrical frequencies question. If all of that tracks.
Yeah, well, I think that the sensor fusion neuroimaging world is where a lot of these statistical methods can be traced, by virtue of the SPM origins. And here, this live stream was excellently prepared for by Ali. Professor Grossberg was one of the relatively small fraction of guests who prefer full-sighted referenced questions before joining, but also he prepared excellent answers, and there was great discussions about the compatibility or reconcilability of art, FEP, ActInf, everything. Alexi?
Yeah, I'm just grateful for your question again, going back to it, and I have the same interest, but you know, come join us on August 23rd if you can on the chaos theory paper. I mean, I think I'll try to talk about how the higher the frequency of the EEG, the higher the Kolmogorov-Sinai entropy, the higher the level of chaoticity. And there's much evidence kind of converging on that stuff. Today on Twitter, of all places, Earl Miller from MIT was talking about beta frequencies governing the exchange between medial prefrontal cortex and right hippocampus for spatial working memory. So that does seem to kind of not only be theoretical, but also confirmed empirically that we have kind of control signals are slower. Think about the brain, you know, subcortical neurons are firing at 1/10 of the frequency of cortical neurons. And subcortical neurons and brainstem are arousing the cortex. They are kind of the blood and the energy, the arousal, generalized arousal comes, you know, that way. And another thing I wanted to mention is about the prioritization of sort of Mark Solms talks in his book about how working memory is a very small space, like 7 chunks of information plus minus 2. And when we feel something, it has to get in the working memory. Otherwise, you know, we have to be conscious of an intense feeling. And ordinarily, for example, we don't like urinate or defecate in public. This is embarrassing. So we hold it, we inhibit the wish. But when people go through like public execution or hanging, that wish is completely released because there is a higher priority. There's an existential catastrophic threat. And that this sort of fear of social embarrassment is completely deprioritized. So it does suggest that we need a very high energy signal to kind of overcome very well entrenched predictions. So it's a vast topic, and I'm highly interested in it. So if you're interested, maybe we can talk and collaborate.
Cool. Thank you. And again, to connect that to the Terence Deacons, like a high energy signal, are we talking about an informative signal? Because an informative signal could just be 10101010 cleanly, or something like that. Are we talking about like a powerful, like meaningful, like just some cultural landmark that has a specific aboutness but isn't situationally relevant? No, the high energy is happening at this higher cognitive level. Might even be a subtle signal informationally, or it might even be a subtle signal symbolically or semantically. But that's the whole thing with like early warning systems, and like, just the movement of a shadow or the rope coiled up on the ground might convey extreme actionable information, whereas there might be something in a different quadrant that's like very clear but not survival relevant.
Exactly. I mean, I think that if you go into like ecological evolutionary goal of mammals to survive and reproduce, then okay, so survive means eat and don't get killed. And so sexual functioning and gastrointestinal functioning is disabled when we are in a state of acute fear. Acute fear takes precedent, because if I'm dead, it doesn't matter. I will not be able to reproduce. So my first job is to survive. There's a prioritization happening, and that's going to be an intense signal that just occupies the entire mind and just casts everything else out, right?
Yeah.
That
I mean, a lot of these, whether we approach it from like a circulatory system or like a more abstract information, like a lot of these patterns are explained or predicted, or so-called paradoxes are kind of shown to be otherwise, when it's like, yeah, you can't have max blood flow to every region at the same time. Like if you could do that, then you would just have some higher level of allocation to do. So yeah, when you're running, your gastrointestinal tract slows down. Like there's just a shunting of resources, and there's a shunting of attention as well. So it doesn't make sense to have a system where equal maximal attention is being deployed. It's just not viable, but we can describe it. So that's like why the ActInf motifs and all of these like concepts, these are our grammar or our ontology that gives us the expressivity that we need to do the modeling. But so we can describe systems that, yeah, maybe there is a system that pays equal attention to all of its 10 ideas, but or not. Or, it doesn't have any ability, an organism that doesn't have the ability to shunt or redirect blood flow or attention, or it doesn't have the ability to do sensory attenuation or something. I mean, you can build it. Okay, a lot of these questions are about specific like variables. We may have come to this one last week. Why is the marginal likelihood called marginal? Does anyone know this or have a thought? Yeah, Ali, go for it.
It's a remnant of statistical theory, because you see, when we sum the probabilities of a given event in a tabular form, the ultimate sum would be written in the margin of the table. So that's where this marginal probability term comes from.
Perfect. Yeah, what a great what a great term. It's in the margin of the spreadsheet when they summed across kind of collapsing on one thing, conditioning on one thing happening, you can collapse across the other dimension on the spreadsheet, and then it's in the margin. Yeah, so many questions. Another kind of clear one. Belief updating about policies. To update beliefs about policies, we find the posterior that minimizes the free energy. Does a posterior at time t become a prior at time t+1? Yes, it does. So like D, we call that variable in the generative model the prior, because it gets the whole chain rolling. But you could also think of this as just like kind of being like a starting position on this unfolding sequence. So here's a temperature in the room, and we're just going to say, well, our data or our modeling started at midnight, and it was 30 degrees. We're just going to inherit 30 degrees if it was a precise prior. Or you could say, we're going to start the chain by pulling from a prior distribution. So we're going to start the chain with 30 plus or minus 10. And then we're just going to let it play on. And then in that situation, with respect to the present moment, S sub t, this is a posterior with respect to what just happened, but it's a prior for what is about to happen. So just like Markov blanket is not kind of absolute, it's about which variable you're talking about. Also, prior and posterior are relative to the incoming observation. So after you've updated the posterior, it's not like you just stop. Then that updated value for the hidden state becomes the prior for the next incoming piece of sensory data. A lot of equations that I hope we can unpack and develop in math group and otherwise, and like annotate richly and make sure that for all the equations that we have those descriptions. And yeah, chapter 4 is a big one. I mean, there's a lot to it and brings up a lot of big topics. That was our second discussion on it. We are close to the end. We'll go into chapter 5 next. Also, I remember, thank you, Lexi. Bronwyn, I think you, some discussions that we had went into the specific message passing neurobiology in the setting of chapter 5. So how should we prepare ourselves?
Yeah, that was a while ago. Yeah, it's a tricky subject. I've been listening and thinking through today. I've just gone back to equation 2.6 because I got a bit confused. But it was just about message passing in the relationship to the reduction of free energy and expected free energy. But I'm still thinking about it, so I might discuss it next week if I come up with something. But I think it's very complex, and then you've got the hierarchical thing happening. But one question I had was that over a synapse, there's sort of two functions. One is a facilitation, and one's an inhibitory process. And I think we don't consider the inhibitory process or ability to inhibit very much. It's sort of all about action. But yeah, I have to think about all that. But that's I mean, in that equation, you've got all of your all of what you were talking about, taking risk. That thing about the cat smell example. But within that selection of a policy for the reducing expected free energy, You want the one with the least expected free energy, but you're also balancing up other factors in terms of the three nested. I think the three nested thing was really interesting because it gave you that hierarchy of habitual responses as opposed to considered ones and higher referential or significant evolutionary considerations. But underneath it is this equation, I think, the relationships between these things in that moment when someone makes a decision. So yeah, it's quite a complex thing that the brain does, really. That's my thoughts.
Oh yeah.
This is
Great.
very basic, but that's where I sit. So anyway, I've been doing other things lately, so I'm a little bit lost, and I haven't had a good relook at chapter 4, but I will between now and next time.
Awesome. Yeah, a lot of ways to go there. This functional, this can apply to a nested system. It's just all kind of abstracted there. And again, this is kind of like that blueprint view. Message passing helps us get there with the how. So it's kind of like the low road, which is where this equation comes from, chapter 2.
Yeah.
It's like it's explaining the how, and then the message passing is like the how on the how. And then also like what you said about one worldview is like the central operator, central governor is kind of being like spurred into action. It's all about like excitatory signaling from the outside, or it having to stimulate a passive exterior through like carrot and stick or just stimulus in general. And then that reminds me of Tom Froese with his guest stream on the eruption, which is like, yeah, what if it's like there's just this like seething activity, and then what's happening is like inhibition and breaking, and then like in those spaces that are opened up through inhibitions and breaks, things unfold. So it's not like the decision making was like shining the laser on where to go. It's like, no, there's more than enough energy to go around, mental energy, and it's just about knowing when to inhibit, when to break.
Yeah, absolutely. So thank you, Daniel. I think the problem is it's not about making the decision, it's knowing when to inhibit. And that's from the work that I do, really is the strong point of inhibition as a very important part of decision making and action in the world, just how we behave. Really, I mean, if you look at the basis of a synapse, you're facilitating or inhibiting, and that's the balance between those two in terms of message passing. But nobody talks about inhibition very often. Anyway.
Yeah, great. I mean, in the number go up world, reward is good, more reward is better, stimulate reward is stimulating, sugar is good, all that. Versus in the predictive processing, at least we open the discussion to both hands of up and down, and stimulate and inhibit, or maybe neither stimulate nor inhibit, just different. Yeah. So we have all the axes we need, and that's why chapter 6 exists, is because so much of the challenge is like, what building do you want to build? So if we said, okay, well, from this, we can optimize it super tractably, it's not going to be an issue. But what is it? What is that model going to be? And how are you going to iterate on that in a real setting? Which brings the whole understanding into action. And earlier, this was just the last paragraph of the book. Active inference is not something that can be learned purely in theory.
No. Boom, boom. No, it's the action. People keep forgetting about the action. The two are entwined. You can't separate any of it. So yeah.
Awesome. Yeah, well, fun fun discussion. Thanks, Andrew, for highlighting the message passing angle, and it's going to be a perfect lead into chapter 5, where we will revisit message passing again from this like nervous system angle.
Yeah. Great.
Okay, thank you
Thank
all.
you very much, Daniel. Thank
Till
you,
next
Karl.
time.
Thank you.
Thanks,
Thank you
everyone.
so much.
Bye.